So here we are at Desmos's default contour diagram. What I would like to show you is that no matter which point we pick, if we start zooming in at that point, what we're going to see is a linear function. So what I'm going to do is I'm going to pick the point 1.3.7. Let me zoom in once so you can see what it looks like there. 1.3.7 is right about here, I think. What I want to do is zoom in at that point, and I'm just going to keep double clicking. Right now you can see that the contours are straightening out. I actually can't see too much about what's going on because I don't have enough contours. So what I'd like to do is add some contours. I have the contours from -3 to 2 here. But if I start zooming in and add lots of contours, the number of contours gets to be so big that it's bad. So what I did do is I plugged in 1.3.7, found out that the contour value there is 0.96. So I'm going to try to focus in on that. Instead of going all the way back to -3, how about if we go back to like how about 0.5 and go up by 0.1s and just see what happens. Like that. Well, I at least have more contours there. If I go to 1.3.7, I start clicking in again, and double clicking again, and double clicking again. You can see that they're looking very linear. This one over here is still curving a little bit. So I'm going to add more contours. And again, I don't want to stray away too far from the 0.96, otherwise it's going to try to draw 1,000 contours. So how about if we do something like this? We'll go, how about 0.9, how about 0.905, ... 1. Nope, I can get a decimal place right there. There we go. Let's see here. Okay, so I have a lot of contours at 1.3.7. I'm going to start zooming in there, zooming in there, zooming in there. You can see that looks very, very linear. It's exactly what I want. The nice thing about having a linear function here is I can start estimating the slopes. M, which remember is the west-east slope, and the N, which is the south-north slope. Now, I have some notes over here that I'm going to run through pretty quickly. After we zoom in until it's linear, which is what we've done right now, we can estimate the west-east slope M. But remember, we use delta z over delta x to actually estimate that, and the definition of the partial derivative is the limit of delta z over delta x, right? So when we estimate the slope here, what we're really estimating is the partial derivative with respect to x. The same thing applies to y. When we estimate the south-north slope here, remember that the definition of the partial derivative with respect to y is the limit of delta z over delta y, but we're using delta z over delta y to estimate these slopes. So when we estimate the slope n here, what we're really estimating is the partial derivative with respect to y. Once we actually decide to start writing down the equation of the plane we get, we see that it's going to be z minus the function value, right, is equal to the partial derivative with respect to x times x minus a, plus the partial derivative with respect to y at that point, times y minus b. There we go, all fixed. Now, if I solve for z, what we're going to get is a different function. Everything after this equal sign right here is a linear function. Is a constant plus a constant times x minus a plus a constant times y minus b. That's a linear function, right? This is called the local linearization of the function. This is the same thing we do in Calc 1, where we zoom in until it looks linear and we find the equation of the line. Now, the line there is the tangent line. What the plane here we get, remember this is a plane, is the graph of a linear function, is actually the tangent plane. But it's actually much easier to estimate and calculate if we zoom in on the contour diagram than if we try to zoom in on the graph. So summarizing, when we zoom in on a graph at the contour diagram, the linear function we see has an equation that involves partial derivatives, and it's actually the equation of the tangent plane.